All right, let's talk about turning pure chance into something we can actually predict. Today, we're going to take a deep dive into the mathematical toolkit that helps us make sense of our incredibly random world, and we're basing it all on a university engineering syllabus. So let's jump right in. So let's start with a classic puzzle. You've got a gambler, and their luck isn't totally random. When they win, their confidence is up, giving them a 60% chance to win the next game. But a loss? Oh, that hits harder, leading to a 70% chance of losing the next game. So with all these hot and cold streaks, where do they end up in the long run? It sounds really tricky, but I promise by the end of this, you'll see exactly how to solve it. So here's our game plan. First, we're going to learn the basic language of chance. Then, we'll use that to figure out how to predict a random world. After that, we'll see how to actually put data on trial. And finally, we'll wrap up with the science of comparison.
Okay, Section 1, the language of chance. Before we can start predicting anything, we need a way to talk about it, right? How do we even begin to describe something as chaotic and unpredictable as randomness itself?
And this right here is the core idea. We can't predict a single coin flip. No way. But we can describe the pattern of 1,000 flips with stunning accuracy. The tools we use for this are called probability distributions. You can literally think of them as the blueprints for how randomness behaves.
And here are some of the heavy hitters. You've got the binomial for simple success or fail situations. The Poisson distribution is awesome for tracking events over time, like how many accidents happen in a year. The normal distribution, that's the famous bell curve you see everywhere in nature. And the exponential distribution is perfect for modeling the time between events, like how long a phone call lasts. Okay, let's make this real with a problem pulled straight from the source material. A factory knows that 1 out of every 10 pens it makes is a dud. So, if you buy a box of 12, what are the actual odds that exactly 2 of them are defective? This is a textbook case for the binomial distribution. See, it's not just guesswork, it's a precise calculation, and it's absolutely vital for things like quality control in the real world. So let's build on that. We can now describe a single snapshot of randomness. But what about a system that's constantly changing over time? Can we actually predict how it's going to behave?
Turns out we can, and we do it using a really cool tool called a Markov chain. The key idea here is what's called memorylessness. It sounds weird, right? But all it means is that the future only depends on where you are right now, not the whole long story of how you got there. It's a simple concept, but it's the engine behind everything from weather forecasts to stock market models.
And this is exactly how we crack our gambler puzzle from the beginning. We build what's called a transition matrix. We have our 2 states, win and lose. And these numbers just represent the chances of jumping between them. So for instance, there's a 0.6 probability of going from a win to another win. And since we know there's a 0.7 chance of going from a lose to another lose, that means the chance of going from a lose to a win has to be 0.3.
Now, by analyzing this matrix, we can find what's called its stationary distribution. You can think of it like fast-forwarding through millions of games to see where the probabilities finally settle down. And the answer? The gambler ends up winning about 36% of the time. So even with all those dramatic streaks of good and bad luck, the math cuts right through the noise and gives us a clear, predictable outcome.
Okay, this is where things get really, really interesting. We're moving from just describing and predicting to actually asking questions of our data. Welcome to Section 3, Putting Data on Trial. This is the heart and soul of statistical inference. Honestly, the best way to think about this is like a courtroom for data. We start with a default position called the null hypothesis, which basically says nothing interesting is happening here, no effect, no difference. That's the status quo. And we put it on trial, and the whole point is to ask, do we have enough hard evidence in our data to reject that default assumption and say, nope, something significant is definitely going on? And this isn't based on a gut feeling. It's a super structured 4-step process. First, you state your hypothesis. Second, you decide on your standard of evidence. How sure do you need to be? Third, you go collect your data and run the numbers. And finally, you compare your result to your standard and make the call. One of the classic tools for this is the chi-square test. It's perfect for what's called goodness of fit. In plain English, that just means checking if the data you actually got matches the data you expected to get. So for example, if you roll a dice 60 times, you'd expect each number to come up about 10 times. A chi-square test tells you if your actual results are so far off from that expectation that you can be pretty confident the die is loaded.
All right, for our final section, we're going to shift gears a little. So far, we've been analyzing data that already exists. But what if we could design our own experiments to get the exact data we need? This is the science of comparison.
The star player here is something called ANOVA, which stands for Analysis of Variance. So what makes it so revolutionary? Well, it lets you compare multiple groups all at the same time. This is a huge deal because it saves a ton of time and, more importantly, it lowers your risk of being fooled by random chance, which can happen if you just compare things two at a time over and over. So here's the key difference. A standard test, like a t-test, is great for comparing two things. Is drug A better than drug B? But with ANOVA, it's like a statistical battle royale. You can compare drug A, drug B, drug C, and a placebo all in one single test, and it will tell you if there's a significant difference anywhere among them. Let's walk through an example. Think of it like a statistical bake-off for plant fertilizers. We want to find out which one is truly the best. You start by doing the experiment and just collecting your raw results. In this case, the growth measurements for plants that got different fertilizers. Then you take that data and run it through the ANOVA process. And this is where the magic happens. It spits out this amazing summary table that neatly separates the two types of variation. The variation between the groups, the part that's actually caused by the fertilizers, and the random natural variation you'd expect to see within each group. And by comparing those two things, ANOVA gives you a clear, confident verdict. In this case, the analysis shows that the difference between the fertilizer groups is way bigger than the random noise. So we reject the null hypothesis. The verdict is in, the type of fertilizer you use absolutely makes a statistically significant difference. It works. So there you have it. We've gone all the way from just describing chance to predicting what's going to happen and even designing experiments to get solid answers. These aren't just abstract formulas in a textbook. They are the real tools that turn uncertainty into actual insight. So I guess the only question left is, now that you've seen the toolkit, what important question would you test first?